Look closely at the seismic telemetry data feed displaying on your control room monitor, 12,262 meters deep into the continental crust. This is not merely a depth metric of a deep industrial borehole. It represents the absolute physical boundary that human mechanical engineering has ever breached. Deep within the Kola Peninsula, steel pipes no longer behave by standard physical laws. At this ultimate depth, the hydrostatic pressure exceeds 120 megapascals. It equals the crushing weight of an entire locomotive concentrated on a single coin. The technical objective was to penetrate the ancient sedimentary layers of rock. Engineers aimed to reach the Conrad discontinuity to study the deep planetary crust. Yet, to achieve this, a colossal surface infrastructure had to be erected first. The monumental Ural-Mash 15000 drilling tower rose high into the freezing Arctic sky, a 64-meter-tall interlocking steel structure, equivalent to a 20-story building. This heavy-duty derrick frame was engineered to support a continuous static load of 400 tons. The mechanical heart of the entire site was a massive 15,000 horsepower electric motor. This power source continuously turned massive steel drawworks to lower the heavy drill string. Under the immense weight of these steel sections, the entire derrick superstructure groaned. Each pipe section was meticulously aligned and threaded by a team of mechanical technicians. These engineers worked in silence, adjusting heavy hydraulic iron roughnecks on the platform. No words were spoken. They only monitored the alignment gauges with absolute concentration. The massive joints were torqued to precise specifications to prevent catastrophic thread shear. Once locked, the drill string descended further into the dark, wet borehole guide. To prevent the entire string from buckling, the vertical alignment had to be perfect. A deviation of even a few millimeters would cause the steel pipe to snap. This required constant calibration of the heavy rotary table supporting the top drive. Meanwhile, let us examine the mechanical design of the drilling assembly itself. Standard drilling methods of rotating the entire 12-kilometer pipe string from the top were useless. The cumulative frictional resistance against the rock walls would twist the steel like paper. Thus, the Soviet design team turned to a brilliant hydraulic solution. They placed the primary driving mechanism at the very bottom of the hole, a high-torque hydraulic downhole turbo drill driven purely by fluid pressure from above. Under massive pressure, specialized drilling mud is pumped down at high velocity. The heavy mud stream forces the internal turbine blades to spin at high revolutions. This kinetic energy is transferred directly to the rotating cutter head at the bottom. Because of this, the 12-kilometer steel drill string remains completely stationary. This brilliant design prevents the massive steel pipes from twisting and breaking. The drill head itself is a masterpiece of extreme metallurgy. It features rotating cones embedded with industrial tungsten carbide inserts. These teeth crush and grind the dense granite under immense mechanical load. Special synthetic diamonds reinforce the outer cutters to resist abrasive wear. Every single movement is closely monitored by digital instruments on the surface. The technical crew watches pressure dials in absolute silence, tracking every millimeter. No conversation occurs. They only communicate through precise hand signals when needed. The engineering tension inside the control room is heavy and silent. To understand the incredible scale of this process, we must look closer.
Standing before the colossal Ural-Mash 15,000, the sheer scale of this Arctic operation is breathtaking.
Let us now dissect the grueling physical sequence of the actual drilling execution. As the drill bit grinds the deep rock, its cutting teeth wear down rapidly. Replacing a worn assembly at 12 kilometers requires a complex physical operation. The team must execute the grueling trip cycle, a process lasting 18 hours. Every single stand of drill pipe must be hoisted up to the platform. Technicians must unscrew each 33-meter steel pipe joint with heavy mechanical tools. The heavy pipes are systematically stacked onto massive vertical storage racks. This massive steel puzzle is handled with rhythmic, industrial precision by the crew. They work in absolute silence, communicating only through calculated mechanical actions. Once the worn-out drill bit finally reaches the surface, it is analyzed. Metallurgists examine the flattened carbide teeth under specialized work lamps. A new, sharp assembly is then bolted onto the heavy downhole turbo drill. The entire process is then reversed, lowering the string back down. During this long descent, The chemical stability of the borehole mud is vital. The heavy fluid must hold the immense pressure of the surrounding walls. Without this critical hydraulic balance, the unstable borehole would cave in instantly. The special mud chemistry must also cool the system from geothermal friction. It carries massive heat away from the rotating metal teeth at depth. Yet, as the project pushed past 10 kilometers, new barriers emerged. Geological predictions on temperature limits began to fail one by one. Instead of the expected 90 degrees, the crust was far hotter. Instruments registered an astonishing 180 degrees at the bottom. At this extreme thermal threshold, rock physics change in strange ways. Under extreme heat and pressure, solid granite loses its brittle structure. The deep geological layers begin to behave like thick, slow-flowing asphalt. The semi-plastic rock constantly squeezes and binds the spinning drill bit. The immense pressure of the plastic stone slowly chokes the lower assembly. Friction increases exponentially, putting extreme structural stress on the metal. The heavy steel drill pipes begin to stretch under their own weight. 12 kilometers of alloy steel now behaves like an elastic rubber band. This massive steel structure can stretch up to several meters under its own vertical weight. Any minor axial misalignment at this depth creates violent, destructive harmonic vibrations. The spinning metal shaft bends and warps into a chaotic helix inside the hole. This leads to the most dreaded technical emergency of all, drill string shear.
The scale of this facility is staggering. These mud pumps alone process thousands of gallons an hour, essential for the ongoing...
The broken lower section drops instantly to the absolute bottom of the wellbore. To recover the lost drill string, specialized fishing operations must be immediately executed. Engineers construct custom steel overshots and mechanical grab spears inside the machine shop. These unique retrieval tools are slowly lowered into the dark abyss to fish. The recovery process requires absolute millimeter precision from the surface operator. The operator monitors tension indicators in absolute silence, waiting for the structural catch. If the mechanical grab slips, the entire borehole could be permanently blocked. Once caught, the heavy load is pulled up millimeter by slow millimeter. Every single joint must be inspected for microfractures using magnetic scanning. The technicians spray fluorescent dye to visualize invisible stress cracks on the threads. Any compromise in structural steel integrity means the drill pipe is permanently decommissioned. These rejected alloy pipes are systematically catalogued and stacked in the storage yard. The persistent war against extreme pressure and heat requires unending mechanical vigilance. Throughout this relentless journey downward, the engineering team gathered invaluable scientific data. They retrieved core samples from deep layers that had never seen daylight. Geologists sliced these crystalline cylinders in the on-site research lab in absolute silence. Under polarization microscopes, they analyzed the mineral structure of the deep granite. They discovered that the rock at 9 kilometers was highly fractured and porous. Even more surprising was the presence of highly mineralized hot water flowing. This completely shattered existing geological theories that deep rock was dry and solid. The presence of free hydrogen gas was also detected inside the return mud. This gas-mud mixture constantly bubbled to the surface, showing active, deep geochemistry. Furthermore, microfossils of ancient single-celled organisms were discovered at extreme depth. These microscopic biological structures had survived under crushing pressures and extreme heat. This proved that biological precursors could endure in the harshest deep environments. These incredible discoveries made the decades of brutal physical engineering entirely worthwhile. By 1989, the Kola SG-3 borehole had reached its final depth, 12,262 meters of unparalleled mechanical achievement. The project eventually halted as extreme geothermal temperatures melted drilling equipment. The solid steel structures could no longer maintain structural integrity under that heat. Today, the massive Uralmash facility stands abandoned in the quiet Arctic tundra. The colossal steel derrick has been dismantled, leaving only concrete ruins behind. At the center of the derelict hall lies the actual physical borehole. A heavy steel cap, secured by thick industrial bolts, seals the dark abyss.
This unassuming metal cap covers the deepest point ever reached by humanity.
It stands as a silent monument to the power of human mechanical design, a testament to the engineers who designed machines to conquer the planet's depths. The physical process of constructing Kola SG-3 redefined heavy industrial limits. It remains a masterclass in mechanical resilience, structural engineering, and sheer determination. To explore more masterfully engineered blueprints, subscribe to Blueprint Flow and join us.